Hi, Professor Torabzadeh. Thank you very much for giving me a chance to recoup my project and try to get my degree. And this will be one of several videos that I'm making for you. And there will be some other videos that I will send you the links, and they will be all about combustion chambers and simulating the flow and the heat in these combustion chambers. And I'll have two or three links that you can look at. One of them shows the flow for a few seconds, is more complete and does look like what I had constructed. All of these are simulations, which means that a computer simulates the flow for that given geometry over a period of time. And it uses streamlines and different color variations to show temperature gradients, temperature and I don't know how it usually I think more red was higher heat, or no, I think red was the lower heat, and the more bright colors like blue, or they show extreme heat. Anyhow, I was looking at some of these simulations that are now on the YouTube, and I'm sending you a couple of them. And the project that I did was 15 years ago, and even though a lot of the stuff about my project is lost or forgotten, when I compare my simulations with what is the best ones on the internet, on the YouTube, I see that my simulation competes or is even better than many of what these guys have made. My simulation was for a combustion chamber for flow and heat variations for 15 minutes. And the program allowed me to take color snapshots. I had to go through the trouble and printing them in color and show them to the chairman then. I had like 15, 20 printouts, and also the simulation was live on the monitor. You could see the flow patterns over a 15-minute period. So it started, and then gradually temperature and velocities and heat signatures, they grew to steady state conditions and stayed there in a steady state until I shut the machine off, which happened after 15 minutes. Now, there is many components to this project, okay, that it's not simply that I would do all the work. First of all, the geometry of the combustion chamber is complex. It's not something that I could construct with the CAD/CAM machine on my own. So the geometry was imported, and this geometry was itself something that could be scaled to different sizes, and you had to choose the sizes. Well, when I was in the University of New Hampshire in 1983, it wasn't done on on smaller computers. By the way, I did my simulation on fast personal computers because I kept going to the Besnard's office where it was connected to the mainframe or a big VAX computer system, and I couldn't really work with that, and the time limitations that I needed for the project were not something that's available. I could go into the lab, which was on the third or fourth floor, and then work a couple of hours. But the project that I did required like 50 hours of work. I finally gave up on their computer, on their VAX system or Unix system that they had. I don't know what they had. And the administrator, Besnard, wasn't always unavailable or not very friendly. So I just kind of dumped him and did a little consideration if another computer that was more acceptable can be used. Now, the speed of the computer is very important, and because the numerical solutions require billions and billions of computations. But I did a little study to see what is the level that personal computer, the chip on it, can handle all these computations. And I reached the conclusion that a computer that I had at the time was 10 years old, but the speed on it was 1.86 gigs, which is pretty fast. I was reading some articles about how fast the computer has to be to handle such calculations. And one article I read said that in the development of PCs, like 20 years ago, 100 megabits computer chip was considered pretty fast. But the author was saying that for most computations, the computations that need a lot of computer power are computations that are for the games. If you remember that long time ago, the games are pretty simple. They're pixelated games like Pac-Man or ping pong, and they required 100 megabits was okay with them. If you wanted something more fancy, you had to up the chip speed. But the author was saying that, well, for really fast games at that time, 186 gig would be really good. It would be okay or sufficient. But these days, even that 3 gigs or higher speed is nothing. For the games that we have now, require a lot of going back and forth between the chip and the memory cards or the game cards. And but at that time, my conclusion from all this was that 186 gig was sufficient, and I ran simpler programs, simpler numerical analysis on my own computer that was like 10 years old, and it managed it. It didn't fall apart. So I started using that computer. It was a personal computer, and I brought that computer with the simulation and the code to the chairman's office, and I ran the code with the monitor, my own monitor, and it showed the flow for 15 minutes, plus all the heat signatures with different colors, and I showed him the printouts of all the stuff, and he said that's fine, but what he did, I don't know. My computer sat in his office, and he just kind of played with it, and I found out later that he has said that this is not enough. I think that he just didn't believe that a personal computer could do all these calculations and do the simulation correctly. And because most of the people of my generation, they only did simulations on VAX or Unix mainframe computers, and I think that's one reason that he didn't accept it. And another reason could be that it was entirely out of his discipline of what he was used to. I will go over my all the courses I've taken in mathematics and in fluid mechanics, heat transfer, combustion, and I have done simulations in many forms. In fact, my doing simulations goes back to 1983. I graduated from mechanical engineering in University of New Hampshire and started taking many courses in fluid dynamics and also CFD, computational fluid dynamics codes. And also back then the codes were not this complicated. We actually used Fortran and BASIC to write our own code. So for example, in one course I took, he would give us a geometry. Usually they were very simple geometries, and we would simulate the heat flow or fluid flow. It was usually just one or the other, because the computations would very quickly mushroom out of control. I mean, when you write these codes, you are really starting from a wall or an adiabatic boundary that chamber has. For example, for the chamber that I did, the boundary walls were the surrounding of the chamber, the inlet and the outlet, and there was a heat source inside, which is comparing it to the real engine. This is baloney. There is no such thing as a constant heat source. The pistons hit back and forth. When the piston expands, there is cooling actually a little bit. When the fuel explodes in the chamber, there is a variable heat. It varies every microsecond to microsecond. So really, with the technology and the stuff that we had back then, this is the best technology and best simulation I could do at that time. And even putting it on a personal computer was a really big stretch to go all that far. We would write the code for the geometry, and it was we had to put it on I don't know what kind of, they didn't even have floppies back there. I would go to a dumb terminal that was hooked on to the Unix or to VAX, which were a mainframe computer, usually kept in a very cool room, and I would enter the code manually into the dumb terminal, and then once it was complete, I could save it in the memory of the VAX, and then you had to go many times to run the code. It was a real a lot of work, and then you would run it, and it would have to be run in a batch mode, which was like the VAX would schedule you for a time where nobody else was using that mainframe. And like say 2 a.m. in the morning, it would run it. And when it ran it, it would slow down the entire mainframe. If you were in the dumb terminal and you were looking at it, you see that it's gonna blink for like 20 minutes before it come back and print out all these grid points with the temperature, velocity, all the important stuff. But it was nothing compared to what I had done later on 15 years ago on my personal computer. It was showed the flow speed on streamlines, showed the coloration, was showed temperatures, and you could figure out from the color what was the range of the temperature. It was a much more advanced simulation to what the VAX and Unix could even muster up. And I think one of the reasons that Besnard was not too cozy about is that he probably grew up with this same stuff and wasn't too crazy about VAX simulations or Unix simulations. So you just generate a bunch of little dots and points and printouts. Well, this situation had improved, but when I went back and I remember and compare my simulations with what's the best that's on the YouTube, on the internet, simulations through combustion chambers, and I see that since 15 years ago, the technology and the way they had done this stuff, like a graduate student did these two videos that I'm sending you. They are not, those two are not mine, but they are, one of them is very similar to what I did. I see that they are more primitive than what I had done. But there is a reason for this lack of development in this technology since like 15 years ago. I think that the best decisions for technology, for making good engines, good machinery, it should be left to scientists and engineers, should not be left to politicians or public views. And for example, with Besnard, I took his rocket class. I see that he himself, he wasn't really doing any simulations. Well, I took a class with Reza Tusi, and he wasn't doing, everything was done analytically with equations, with writing down Navier equations, and at the end of the course, he would kind of come around to this idea of, hey, you know, we can solve some of these Navier-Stokes equations by writing them down as difference equations. And then he would do a simple example and show, but as soon as it came down to wanting to calculate the grid points, you see that his grid points are all very far apart, and if he wanted to do calculation even for a simple grid points like 20 or 100, he would be in the class for like 20 hours, because once you calculate one step distance from the adiabatic wall and 1 step time distance from the t equals 0, then you'll get 1 set of grid points. And then if you want to go another step, you have to use all those results to go into the second grid points and then go to the third grid points. And if your time steps and distant steps became shorter, became like, well, in my simulations, I did like 0.001 centimeter, something like that, or meter. Well, that's a lot of grid points right now. But I think I was using meters or centimeters. 10 to the minus 3 meters is a 1 millimeter, and time distance, time progression, delta t of 0.0001 was the maximum. Mine was like something like that, and then simpler simulations would be like 0.001 second. Okay, so imagine you have 10,000 points at like 10 to the minus 6 meters grid size, and you had like 10 to the minus 4 100 microseconds yeah, that's a pretty small step size. So you need a massive computational power to do all this stuff and progress in. Well, my computer didn't freeze like VAX or like a Unix. Unix, you can tell that the processor was just it's like the processor was just freezing, even though it was a huge processor. It had a huge speeds. You could feel it slowing down significantly, like, you know, for several minutes it would just regurgitate all those numbers. And when I was in University of New Hampshire, I was also in the graduate programs there, and took a lot of courses in engineering, graduate engineering. I took a lot of courses in math even before getting there, and then I came to Cal State Long Beach. I've taken so many courses in engineering, in mathematics, in you name it, anything in fluid dynamics, advanced fluid dynamics, combustion, gas dynamics, heat transfer, advanced heat transfer. I mean, this discipline, I have it by the balls. I mean, well, now I saw in the graduate program that they had a whole new discipline for mechanical engineering, and that's called the simulation discipline. That you just instead of making a product or device, you simulate it on the computer. And even before you make the device, that your simulation is almost most of the engineering. Well, I was taking class with Besnard. I saw that even for simulation of advanced rockets, he would construct the chamber, and one side of the rocket was affixed massive beam that had gone straight into the ground. So the rocket would fire up for testing, and it wouldn't be able to go anywhere. The massive beam would prevent the rocket from going anywhere. But this is their experimental way that they could see how this rocket behaved, and also all the equations and stuff that he wrote and did, they are even more primitive than what Tusi had done, or other professors there struggling to get the names right. It was basically just like a wind tunnel experiments. There was no simulations. Everything that was simulation is maybe 10 years behind what I had done in my project. And the same that I come and see what's going on with the simulation, with the people who have done it and put it on the internet. So they are 15 years behind me. Well, at the time, and this happened even after I graduated from mechanical engineering in University of New Hampshire in 1983, the stupid Americans, they went into this massive mania, and they sold and they shut down many of their industries. For example, I went and worked for Simplex, which was a company that made wirings and connectors. The company is completely sold to Koreans or Chinese. Then I went and worked for Gould, the fuse company, and they made very heavy-duty fuses and relays, and that company just completely shut down. I came to, I was in the city of Orange. I was trying to take the bus, and right by the bus terminal there was this massive building that used to hold a manufacturing company for another wiring company that completely shut down many years ago, and the building was just over there. Just these people are totally retarded, and also their hostility towards fossil fuels and towards engines that like burn gasoline or methane or natural gas, and you see that the car makers they did not advance these technologies. Most of the engines that came out later on, they were a really bad replication of what Ford, the motor company, had made, or what the technology was there. After a while, well, let me tell you what the engine manufacturing companies and Ford itself, they found out from doing surveys with their customers. Prior to making this stupid survey, they continuously improved on the engines, and they tried to make more power, or some of them, they have developed the engines to a level where it can go with a long time, like 1 gallon and fetch up to 200 miles per gallon. The engine efficiency had gone that far. But they did this survey asking their customers questions about engine performance. Would you buy a car that was like this or not? And they found out something terrible. They found out that only 3% of their stupid customers remotely cared about the engine or the efficiency or the mileage per gallon or none of that shit. Their executives, they're very short-sighted people. They said, oh my God, nobody cares about this technology that we are spending all this money on. And then also their oil companies and gasoline production companies, they did not want car makers in the United States to make cars that were very efficient. They get huge gas mileage, then they couldn't sell all these gasoline. And then it became like a huge mania with them. And then they were, oh, we found something. This is God gave us this information, and they started dumping this research, this technology. Many of them took their engine productions and car manufacturing into other countries, Mexico, China, and they just spit out replicas of all their engines. But those people, they were not as stupid as Americans, like Honda or Hyundai or Germans. They kept tweaking the engine, the combustion chambers, improving them. And like Honda engines or Toyota engines are like generations ahead of United States engines. But when you see from this era of when this stupidity began, you see all the American cars, Dodge, Chevrolet, they're all making these gargantuan cars. They all have like at least 6 or 8 engines, chambers, combustion chambers or cylinders, and all they focused on was now how to make more ashtrays available in the car, more leg rooms, more everything became something like a woody cars, like. And well, I was sitting in one of the classes, and I was looking at all these books, on the research books that were on the little library, that I see that nobody would ever go and touch them. And I was in the gas dynamic class. I was like, where did all this research, all this stuff, where was it dumped? Where was it? And then this is also another mania evolved with these people. And all the decisions they made with manufacturing and with engines, with technologies, it came from this mindset, which is very retarded mindset. One thing that evolved in all this American stupidity was the hatred of fossil fuels, hatred of CO2. And they all tell each other, well, when the level of CO2 increases in the atmosphere, oh, we are all going to die, and the temperature of Earth is going to, we're all going to be fried. And what are we doing to ourselves, to our children? And well, when I took combustion, and we were actually studying the pollutants that come in from combustion engines, CO2 is not a pollutant. CO2 is actually the food that many plants absorb. And in the geological history of the Earth, every time the level of CO2 in the atmosphere has dramatically been lowered because of the plants, then that's the onset of ice ages. The ice ages cause the plants to die. Then when there is a fire or something like, or a volcanoes activity, then the CO2 levels increases dramatically, and then more it becomes, planet Earth becomes warmer, and then more water and land becomes available, and then there is more growth of the plants. And then this is like a thermostat, a cycle that we keep going from heat to ice age to heat. And in fact, the average temperature of planet Earth has been at times several degrees higher, and nobody completely died off. I am sending you a link to a video I made. It's called CO2, which is a really nice study on the effect of CO2 on our planet. We do not need to be afraid of combustion, afraid of fuels, afraid of kerosene, afraid of methane or natural gas. I was taking the bus the other day, and on the bus, this huge engine, it was saying near zero emission, near, which means almost no emission, okay, which is mostly water and CO2. And it's powered by LNG, natural gas, which is mostly methane. Methane is a very plentiful. There is so much of it around, and when methane burns, oh my God, this is a beautiful, beautiful fuel. And when it burns, it produces pure CO2, which the plants eat. It produces a pure H2O, which is like anybody uses. If H2O got into the atmosphere, oh my God, it's going to make it a little cooler. Why am I sitting and worrying about that? So I would not use these cultural stupidity and values that the Americans and their politicians have as a guideline to make engines, to use fuel. In a while, they were also trying to suppress Iranian or other countries' fuel production or production of raw oil. And we Iranians, we lost so much income, and I think that we're gonna give them back some military response for all this damage that they have done to our petrochemical and oil industry. And we should not care. We should not. And also, I totally oppose technology suppression by the Americans, suppressing purification or refinery machinery. All these devices and technologies that allows us to use this very good old technology. Combustion, even though it's a very old technology, it has been perfected. There is so much research that that somebody just dumped it, just like those books on like, we don't care. We are the new people. We'll go get lithiums and put it in all these junky cars. And if the lithium gets exploded by the Israelis, oh wow. Well, before I quit on this, I want to go through some of the mathematics that has to do with simulation. And in many of my courses that I took, we would use a complete set of Navier-Stokes equations. And Navier-Stokes equations are developed in two distinct forms. One form is the integral forms or summation forms, which is written for like a control volume around the combustion chamber. Imagine you draw an imaginary box around the combustion chamber, and you write equations. Summation of mass must be zero. What's coming in must be going out. Mass is not produced or destroyed. There is no nuclear fusion or fission going on inside the combustion chamber. So this is the one set of equations which are written in summation form, in integral form. The integral rand itself is the same as the sigma, which is the same as we add all the masses. Well, another set of equations that comes out is the summation of momentum in this combustion chamber, and that must be zero. The momentum of coming in must be equal, otherwise the combustion chamber would be flying, or it would be a rocket. It would be or it would be like a Besnard rocket. It would be fixed at the end with a massive beam going to the ground, and all the forces and kick of the rocket would be we're trying to move this beam into the moon. Okay, that's the second set of equations. Then there is another set, let's see, mass, momentum, and also forces. All the forces must add up to zero. When you write this equation, you have to take everything into account. All the flow, the velocities of flow which impart momentum, and the acceleration of fluid which imparts forces. Those, you have to take them all into account, and then you will be generating a whole set of Navier-Stokes equations that are written in the integral form. Another form of Navier-Stokes equation that we use, and this is the form that you must use if you are using simulations. You cannot use the integral forms. Integral forms have another use. I will explain it to you. Another form is when you look at inside the combustion chamber and you imagine an imaginary particle that's inside this chamber. This is not a molecule. This is just a small area or a small volume which we consider a particle for our purposes. And you will write all these same equations, force, momentum, and mass for this particle. And that generates a whole set of Navier-Stokes equations, which are written in partial derivative forms. Everything is partial, so you have to know partial differential equations and how to solve them. And they are not very easy to solve. They are extremely difficult to solve. When you write Navier-Stokes equations in the integral form, in the summation forms, it gives you a bunch of equations, and these bunch of equations, they are simpler to solve analytically, which means that you look at this combustion chamber and you can use the restraints on the combustion chamber, the terms that relates to those restraints, to simplify these equations and make them very simple so they can be solved analytically. For example, in the Besnard rocket, with the rocket that just has its tail, its head just buried into the ground with this massive beam, well, the restraint, the front of the rocket, where it's just, you cannot go. This means that the summation of force at that point is zero. That will drop out a lot of terms in the Navier-Stokes integral form of the equations. And then now these equations you have to look also at other restraints. For example, if on Besnard, he without knowing, he had made one of the walls adiabatic by employing a state-of-the-art NASA wall, which nobody uses on rockets. Made it adiabatic. The contour or the outer wall of the rocket had constant temperature, the same as the ambient temperature. So this is an adiabatic wall, and depending on how far the temperature rises inside the chamber, you could guesstimate the temperature inside the chamber wall and use that as a restraint, as a constraint to simplify your integral form of Navier-Stokes equation to a point where these equations become something that can be solved analytically. And even these simplifying assumptions, and they do not really help that much. The equations are extremely difficult even at that level. Another example that we used in the shock regiments on a rocket, well, the cone of the rocket, there is no velocity. Nothing can go inside the cone, or the gases have to go around it, because the cone has static temperature, which is the static temperature the gas kicks at it. Okay, so also right in front of the cone, if the velocity is very high, there is shock waves. Okay, we could use all these geometries and all these shock properties to guesstimate the speeds or write the equations in much simpler form. I'm using the word much simpler in a relative sense, okay? And that's not really simple. Well, imagine you have like a fluidic device or pneumatic device, and where on one side a very heavy viscous fluid is coming in, and the configuration boosts the pressure that comes from this nozzle, and this massive pressure that this viscous fluid has pushes the piston-like device, which is actually what does the lifting. For example, on these garbage trucks, you see there's this massive lifts. They lift tons and tons of cargo up. Or, for example, in rocket launchers, you see the Hezbollah rocket launcher, the lift comes up and lifts. The rocket is originally on the flat, but this lifts it up to a standing position. When the fluid enters, okay, it is still subject to Navier-Stokes equations. Okay, so If for such situations, some of the terms of their respective equation, Navier-Stokes equation simplifications, there is some higher order terms too. There is like a first order of pressure, or first order of velocity order in that equation. Now, if this, when the operator moves the lever and wants to lift the garbage container or lift the rocket to the standing position, if these second order or first order other terms inside the equation of that fluidic device, if they are even significant in some ways, then you see the rocket is like dancing, like it's shaking to get up to that position. Okay, that is very bad. That means there is transience inside that system. It is now working right. So you must go back to the equations and beef up the damping, the stiffness of the system, which is dependent on the fluid viscosity, to massively to stop these transients. You might have to increase the pressure inside the chamber, but well, enough about the integral forms of these equations. When I was in the undergraduate degree in University of New Hampshire, we had a final project, and the final project was a work and model a Ford engine that they had brought into the lab in the University of New Hampshire, mechanical engineering, and we all were messing with this thing. So all the major properties of this engine were determined by tachometers, which means like it measures the rate of turning of the engine or the cam that it was using to turn the wheels. The temperature inside the chamber, the rate of piston going up and down, the rate of heat generation, the rate of fluid flow, the rate of exhaust. Well, the first half of the course was like, oh, we know what we're doing. We're gonna write all these equations. We write the Navier-Stokes equations for this totality of mass in their integral forms. We'll simplify it, and the old engineer was there. He was doing all this stuff too, and he was showing us this is what it happens. Well, in that course, half the students would drop out the first 30 days. I cannot do this. So the very bad thing about these equations were that everything, it was like 20 different equations, analytical equations. There was all these terms, okay? Everything was related to everything else, okay? But at that time, they didn't have a very good math lab or computer simulations, or you couldn't do matrices on the computer, or some people knew, other people didn't know. And what the professor tried to do, I don't think he knew what he was doing himself, but he thought that this is what we have to do. And we wrote these equations, and the final relation or anchor to reality was anchored to tachometer speed, the flow of gasoline into the engine, the flow of air, the speed of those, what else? exhaust velocity, all this stuff. But these were things that at that time Ford could measure these things. There were devices, for example, the speed of the cam they could measure with some kind of tachometer, which measures the speed of rotation. Okay, and anyhow, it was a huge mess. We all work on it, and like in teams of 3 or 4, and I know that almost everybody in the class was in one form or another was cheating, and they all had paperwork from previous students that had passed the class. And out of the half of the class that survived and was coming towards the end of the project, our professor, he gave like a quarter of the remaining, of the half quarter got an F. They had to repeat that course because they couldn't figure out what the hell is related to what the hell. All these analytical equations were like going anywhere they wanted, and the other half, the other quarter that survived and got a passing grade, like I think 12.5% got a D, but they passed the course. And I was working with this group, and I didn't know what the heck was going on. I was just drawing all this stuff, log paper after log paper, showing all these things, and I think we got C. Well, we've passed. But using the integral form of Navier-Stokes equation to look at systems, heat transfer or fluidic systems is painful and very complicated. And towards the end, when I was in the University of New Hampshire, I took a course in pneumatic, which is like studying devices that use air by different geometries of the nozzle and the pressure of the inlet air. You could do some, for example, you could use a device as like, a lug nut opener. Have you seen the tire shops? That's a pneumatic device. The air comes at high pressure on one end, and it becomes rotational torque on a lug nut, and it opens up the lug. Now, imagine trying to model that using Navier-Stokes equations, and I don't think many engineers are very successful in that because it's very difficult. But one thing I remember from this teacher is that he hated these first and second order terms that are in integral form of Navier-Stokes equation, and he was always trying to see what he can do. I think so much cheating was going on in that class. We were just let's just bring this down, like, so we can model it as something that's linear, like F equal Kx. Okay, that's a linear relationship. But this is a really very unreal kind of simplification for something that's running Navier-Stokes regime. Imagine you're a truck driver and you go in the interstate onto this weight machine. Have you seen? There's like this big platform, trucks go over it and stand in the middle of the platform, and you can see there is a boundaries is sitting on this massive lifters, but they are what's the word? KX devices. Massive springs, okay, springs. And what the basic idea for these things is that they're supposed to go certain amount lower and not too much, and then you can tell how much weight is on the truck. But you cannot have just these springs. You must have a lot of dampers on the. Otherwise, if there is first order, second order terms in this Navier-Stokes regime, you'll see the truck driver go on the lift and then go boom, 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 boom. Like about half hour later, it will slow down, and then you can measure the weight. But you can't do that. So this is basically what was going on in that class. Is do anything you can, anything, to get rid of these first and second order terms in the Navier-Stokes equations that are in the integral form. And when you're doing simulations, you're not doing that. You're writing the partial differential equations in a difference form. You take into effect the first partial derivatives and the second partial derivatives. But in this way of doing things, you are not doing the calculations. You cannot. Human cannot do these many calculations. I mean, there were initially scientists that did some, like Tusi would write like, hey, this is the idea. This is what we want to do, okay? It's theoretically possible, but I'm not going to do it. I don't have time. I don't have 20 hours of time here. Well, some mathematicians, they did it. They did, but for a smaller number of grid points. And later on, I don't know if it was 20s or so, in 1920s, that they hired a whole bunch of women to do all these very painstaking calculations. Because once you do first set of grid points with the first time step, then you have to do the second if you want to go in the direction of distance or go in the direction of time. But imagine your distances are not just one in the x direction, they are in the y direction, in the z direction, the time is smaller. The calculations very quickly blow up. You cannot do it. Humans are not able to do all these calculations. And back then, they had to use supercomputers. They had to use the first computers, even the binary. And I think the first computers, mini computers that came out, PDP could do some of this stuff. But the PDP-11, the writing programs, which was in machine language, was a bitch. I remember in the University of New Hampshire spending nights, like all night, writing machine code, all night. And many times the computer didn't like the code, or the computer misinterpret the code that you have written because the machine code meant something else to it. Go and do all these other stupid things. Things improved with the Unix and VAX and the dumb terminals. I remember I was in a side room in the University of New Hampshire, and we had all these stacks and stacks of computer manuals. So the way these stacks worked, they were printouts. Say, for example, you had one geometry, when you opened up this big manual, which was really computer printout sheet, you would see a certain geometry. For example, you would see like a parallelogram or like a long pipe with inlet and outlet. A lot of them were not three-dimensional, they were two-dimensional, but they were kind of skewed to become three-dimensional, I guess, or the plate distances were small or can be neglected. Really, it can be neglected, okay? And the geometries were marked as like A, B, C. So when you want to run this particular code, say the code was called Hassan, the lunatic mathematician. Okay, you would have to, it would come in and spit out a request form for the A, and you put in the A value. Then you put the B value. Then you put the C value, and then it will come in and ask you, what's the inlet velocity? I would say like this. Outlet velocity is like that. And then how many grid points do you want? I would say like 10,000. I think 10,000 was a very large number for that time. And then what's your delta t, which is the time step that I would take to calculate this simulation. Then you will give it that, and then you had to do all this stuff at the dumb terminal where the main code was written and resided as a resident program. And then once you did that, you could assign it. You would better assign it to a batch job, but sometimes I didn't. It would you put in all this. You see the computer go, oh my god! And about half hour later, after you got a couple of coffees and stuff, it would come in and you could tell it, print me all these results, and the results were these massive printout of numbers from grid point to grid point, and you had to go figure out how the grid point would look like. Or later on, they did a little bit of representation as on it. It all really sucked, and it was very difficult. I think early scientists, they generated simulations for shock waves in front of planes and all that. Well, in the 1920s, there was another attempt to tabulate results and show the results, and they had two ways of doing that. One was by wind tunnels, and they would run different wings of airplanes or shapes of submarines or boats, and these were markdowns. Like, you couldn't really take a huge 707, 777 plane wing and put it in the wind tunnel. You had to scale it down, and there was all these formulas relating the scaled down version, everything, pressure, to the actual that it might be on a real wing. Scale down on scales, wing lengths. It was a huge mess. There were tables showing all of this stuff, and they would run for different speeds, subsonic, laminar flow, and faster on these wings, and then they would generate their own table, similar to how I generated flow properties on a simulation inside between two plates. Okay, they would they would generate this table. There are huge books of tables. Shows if the wind speed is this, the wing aspect ratio is that, and the la la. The velocity and dead pressure points would be here and here, and then that would be the extent of that. And then, but because there was such varieties of wings and configurations, they did a little bit of analytical cheating too. What they did was they would have these cylinders. They were just cylinders of different sizes and aspect ratios and lengths, and they would put them in different velocity fields or pressure fields or fluid fields, and measure experimentally what happens to the flow, where is the stagnation point, where is the flow velocity on top, on the bottom, and then they would use a form of mathematics that comes from complex number theory. It's called conformal mapping, which means like they would map out, they would use a function, a very complex function, to map out this cylinder or the wing. They will map out the wing, the points of the wing, by this complex function that was specially designed to correlate the cylinder to the wing type to this cylinder. Okay. Also, they would map out all the velocity and fluid flow, all that shit into the wing. So when they finished their measurements on the cylinder, they would generate massive tables for different wings. To me, that's the most obscene kind of cheating that there could be. But they were poor chaps. They didn't have any such thing. The technology for wind tunnels was primitive. They didn't have money. There was this incessant demand by military, by manufacturers, to get this data for different wings, for different submarines, and so that's how they generated their best data. It wasn't that great, but they did a lot of factoring to get as close. And then, well, today I think the reason this technology of simulation is going to totally take over engineering, because we can have the machinery, the mathematics do all the work. We don't have to like write equations and do all this stuff. But as I said before, the engineering decisions here in the United States and scientific decisions are not made by the scientists or engineers. In fact, this technology, Yankee technology, military technology, it has died. It actually died in the 70s and 80s. And other countries took this technology and did tremendous things with it. Now you can see Iranian military is making scramjets, things that Americans don't even dream of. Same with Chinese. They're making radars that sees anything. Iranian car companies are still in the hands of some of the mafia from Shah's time, but I think they are making trucks, massive trucks that carry rockets or military equipment. Those are very good engineering, and It will go everywhere. It will go, and you'll see that a lot of these technologies that the Americans dumped, and they're going to have gone into other countries. Who knows who's making these massive bus engines, zero emission on all these huge machinery. This is as much as I got for this video. Along with this video, this is going to be on my YouTube channel. I'm going to send you a link to another video. It's called CO2, and 2 links to the other simulations that were kind of similar to mine, but they're more primitive. And I plan to get my MS degree and also go study mathematics and simulation, numerical simulations, either in Cal State Long Beach if they have such a thing, or in a PhD program. And I'm not stopping because this discipline, it was very difficult, long time to master it. I will now waste it. I will not do this stupid Yankee thing, just dump the stuff everywhere. Thank you very much. Please write all your questions, and I will answer them via email, where the links to these videos are coming to you. And if you need documentations, that's no problem. I will have many examples and documentations that I will give you. Thank you very much, Professor Torabzadeh, for all the time and effort. And once I get back into the program, I will be taking many courses in the energy field, in electrical or in mechanical engineering department. These days, because I'm older, I get free tuition, so you're gonna see me. Thank you. See you later.